Hey, it's Paul from howtonetwork.com. I'd really appreciate it if you give this video a like, thumbs up, subscribe to the channel, hit the notifications. It really helps us with the YouTube algorithms and it helps cover a bit of ad revenue so we can pay for more videos to be created. So if you do that now, I'd be very much in your debt. Enjoy the videos.
Hi, this is David Voss, CCIE 11372, and in this video we're covering concepts of routing protocols. Specifically, we'll be covering static and dynamic routing, and then within dynamic routing we'll be talking about some of the design considerations you need to take into account when dealing with dynamic routing protocols, when choosing to use dynamic routing protocols, and understanding some of the different concepts which are foundational to understanding which routing protocol may be the best to choose. So this lays a foundation for you prior to digging into each individual routing protocol in the later videos. This lays a good foundation for you to begin. Network designers should know the key characteristics that different routing protocols have, because they will be in a position to recommend specific routing protocols for different projects. The first key decision criteria is figuring out whether static or dynamic routing should be used. Static routing implies manually defining routes on devices, and dynamic routing implies a dedicated routing protocol that will build a routing table. Now, even though static routes may not seem necessary in modern networks, there are certainly situations in which they can offer granular control and optimization of the information learned by the routing protocols. They can be used in conjunction with dynamic routing protocols to reach specific networks or to provide a default gateway. This is obviously useful in situations where the destination network is not a part of the routing protocol database. Another scenario in which static routes are used is to override some dynamically learned routing information. Static routing can also be used in the form of floating static routes. For example, when you set the administrative distance of a particular static route to a higher, which is a worse value, than the administrative distance value of the same route learned via a routing protocol, and this would be done for failover reasons.
Cisco wants you to be able to identify the attributes of routing protocols so that you can make the correct design decisions. The fundamental question is, which routing protocol should you use? When answering that question, you must keep in mind the following characteristics of routing protocols. And Cisco wants you to remember all of these. First is scalability. How large is your network now? How large will it become? This is important because there are versions of RIP, or actually all versions of RIP, have a maximum hop count of 15 routers. OSPF and EIGRP scale much better, and BGP is the primary routing protocol used on the internet, so obviously it scales very well, and many companies in fact use BGP internally for that reason. Vendor interoperability. Will you be using all Cisco routers on your network, or will it be a blend of Cisco and non-Cisco? Why is that important? Well, RIP and OSPF work fine regardless of vendor, and now even Cisco has taken steps to ensure EIGRP can be used by any networking vendor. The question is, do they support it? RIP and OSPF and BGP most likely, EIGRP maybe or maybe not by non-Cisco vendors. IT staff's familiarity with the protocol. You and the IT staff at your company might be much more familiar with one routing protocol over another. I worked at a company where we had an internal debate over EIGRP versus OSPF. And the tipping point for the conversation was, what protocol do the engineers already know or want to learn better? It was OSPF. And therefore, that's what we went with as far as our design decision. That was the tipping point. You will have the same debates internally and should be prepared for this in your decision-making process. Speed of convergence. A benefit of dynamic routing protocols over static routes is the ability for dynamic routing protocols to reroute around network failures. When this failure occurs, the network recalculates and reaches a steady state condition. This is called the state of being a converged network. The amount of time for the failover to occur is called the convergence time. Now, some routing protocols have faster convergence times than others. This is important because when a network is not in a steady state, data can be dropped or looped within the network. You should know that because RIP and BGP might take up to a few minutes to converge. By contrast, OSPF and EIGRP can converge in just a few seconds. The capability to perform summarization. Large enterprise networks can have routing tables with many route entries, and network summarization allows multiple routes to then be summarized into a single route advertisement. So it reduces the number of entries in a router's routing table. That eats up less memory, and also CPU because it reduces the number of network advertisements that need to be sent. And that can obviously increase convergence time as well. Here's a perfect example. Let's say we're looking at the routing table of a core router, and it knows about all the branch offices. And let's say there are 255 branch offices, and each are allotted a /24, and they're assigned a 192.168 x.0/24 network. Now, sure, the core router has individual entries for all of these routes and knows how to reach all of them through separate interfaces or tunnels. But all of these routes do not need to be passed individually throughout the network onto a neighbor through a route advertisement. They can be summarized using one summary route, 192.168.00/16. So as you can see, using summarization, we're saving a lot of memory and CPU by simply summarizing all of these routes into one single route. Interior or exterior routing. A key term you need to understand is AS, which stands for Autonomous System, and this is a network under a single administrative control. A network might be a single AS, and when it connects to, let's say, another network, let's say an internet service provider, then it's connecting to a separate AS. When you're selecting a routing protocol, you need to determine, is it running inside your network or will you be running it with somebody outside of your network? To answer the question as to what routing protocol you should run, you need to understand if you need an IGP, an interior gateway protocol, or a EGP, an exterior gateway protocol. An IGP exchanges routes between routers in a single AS. Common IGPs are EIGRP or OSPF, and then RIP and ISIS are also used, but not as much. Today, the only EGP in use is BGP. But please note that BGP is sometimes also used as an interior gateway protocol as well. There are two types of routing protocols. The first type is distance vector. Distance vector routing protocols send a full copy of the router's routing table to directly attached neighbors. Now, obviously this is not very efficient because it's sending information to a neighbor even if the neighbor already has that information. This can lead to slower convergence time. With slow convergence time, you then can introduce routing loops. The routing protocols that are considered distance vector are RIP and EIGRP. There are two mechanisms that you can use to deal with routing loops that Cisco wants you to know. The first is split horizon. This prevents a route learned on an interface from being advertised back out that same interface. I'll show you a diagram in a minute so this makes more sense. And then there's poison reverse, which causes a route received on one interface to then be advertised out the same interface with an infinite metric so that nobody actually wants to use it. But let's go ahead and take a look at the diagram so we can better understand the issue with routing loops and distance vector routing protocols, and then what we can do about it with split horizon or poison reverse. As you can see here, we have a basic point-to-point network, router 1 connecting to router 2 over serial interface, and then a network 192.168.1.0/24, which is then advertised out serial 0 over to router 1. Router 1 then learns that route and places it in its routing table, as you can see here, with a metric of 1 hop. Now, what if Ethernet 0 on router 2 were to go down and the network were no longer available? The problem with distance vector routing is that router 1 is going to send its full routing table over to router 2. Well, router 2 does not know about 192.168.1.0 anymore, So when it receives the subnet advertisement from router 1 of 192.168.1.0, it's going to accept it and place it in its routing table with a metric of 2. And this is where we introduce routing loops. Router 2 will then forward traffic over to router 1. Router 1 thinks it can reach that network via router 2, and traffic will then loop between the two routers. This obviously is not ideal. Now you've already learned about the two solutions to deal with that, and you'll need to know it for your CCNP exam. Split horizon will prevent a route learned on an interface from being advertised back out that same interface, and then poison reverse, which causes a route received on one interface to be advertised out that same interface with an infinite metric. The next type of routing protocol you need to be aware of is the link state routing protocol. Routers send link state advertisements, or LSA, to advertise the networks they know how to reach. So they don't send the full routing table, just the networks they know how to reach, and only when there is a change in the topology. They only exchange full routing information when two routers initially form their adjacency, but from there on out, it's on a need-to-know basis. The routing protocols that are link state routing protocols are OSPF and ISIS. And the final type of routing protocol you need to know is path vector. BGP is path vector, and it includes information not just about the neighbor, but the exact path that packets take to reach a specific destination network. So when you do look at BGP advertisements, you can see exactly over what autonomous systems that traffic is flowing over.
So here's what you've learned. You've received a foundation for understanding routing protocols that will be helpful not only in your CCDB exam, but also as you learn additional information about each routing protocol as it applies to your CCDP architecture exam. Good luck in your studies. Hi, this is David Voss, CCIE 11372, and in this video you're going to learn about route manipulation. You will need to understand on your architecture exam at least the basics of route filtering, redistribution, and understanding how summarization works. Any of these are fair game on the architecture exam. So let's go ahead and dig into each one of these, understanding you may already know these from your previous studies. But if you feel like you're weak in any one of these areas, this video is definitely worth watching because you will be asked about these topics. So let's go ahead and begin with summarization.
It reduces the number of entries in a router's routing table. That eats up less memory, and also CPU, because it reduces the number of network advertisements that need to be sent. And that can obviously increase convergence time as well. Here's a perfect example. Let's say we're looking at the routing table of a core router, and it knows about all the branch offices. And let's say there are 255 branch offices, and each are allotted a /24, and they're assigned a 192.168 x.0/24 network. Now, sure, the core router has individual entries for all of these routes and knows how to reach all of them through separate interfaces or tunnels. But all these routes do not need to be passed individually throughout the network onto a neighbor through a route advertisement. They can be summarized using one summary route, 192.168.00/16. So as you can see, using summarization, we're saving a lot of memory and CPU by simply summarizing all of these routes into one single route.
So that's summarization in a nutshell. The next topic we want to cover is route filtering. Let's go ahead and discuss this topic. So let's draw out this concept of route filtering just to make sure we understand it before we actually program it. So let's say we have two routers, and this router has 4 routes in its routing table. Now let's say this router has 2 other EIGRP neighbors as well, and he intends to send all 4 routes to these 2 neighbors, and he wants them to know about all of those routes.
Now let's say in this environment that we only want 2 of these routes to be known over this path, and that we do not want the router at the other end of this path to know about any of the other routes. What we need to do is we actually need to filter, and EIGRP allows us to filter so that one router only knows 2 routes and that the other 2 routers know all 4. EIGRP filtering allows us to do that. Now we can put a filter on this router here and deny one of those routes to say, you know what, we don't want to know about that route, and filter that out as well. So that's what we have for route filtering. The next topic we want to discuss in this video, and it's the final topic, is redistribution. Let's go ahead and cover this at a high level, but at a level at least granular enough so that if you do get asked in your architecture exam, understanding it's not a highly technical exam when it comes to asking you about coding or specific commands, but you will have to understand how to answer questions about redistribution at the level you're going to learn in this next segment. So let's go ahead and dig into redistribution. Now let's just do a quick review of redistribution. Let's say we have 3 routers that are connected, and in the middle router is connected to one router via OSPF and the other router via EIGRP. The EIGRP router knows of routes 1 and 2, and the OSPF router knows of routes 3 and 4, and the middle router, because it's running routing protocols with both, is aware of all 4 routes. But let's say we want the EIGRP router to learn routes 3 and 4, and we want the OSPF router to learn routes 1 and 2. What we would need to do is redistribute one routing protocol into the other. So we would redistribute OSPF routes into EIGRP, and then that router would learn routes 3 and 4, and then redistribute EIGRP routes into OSPF, and the other router would learn route 1 and 2. Now that being said, maybe you don't want to redistribute all of your routes. Redistribution can be filtered. So let's say we just wanted to filter out one of those routes and we only wanted to share route 3. You can do that. Redistribution also allows you to tag routes. So if you wanted to tag a route, let's say tag 100, it would be known by that router as 100, and let's say the other routes 3 and 4 were tagged as 50. Then if these routes are shared throughout the network in the OSPF area, they would keep these tags, and they would be aware of who is tagged as what. Now this could become important downstream. Let's say you had a router with a rule that said, I am only going to allow routes with a tag of 50. I'm going to deny anything with a tag of 100. That allows you to filter routes not based on subnet or prefix, but simply on tag. So redistribution can be pretty powerful in managing your network. So here's what you've learned. You've learned about route manipulation. We've covered summarization, route filtering, and redistribution. All of these are fair game on the architecture exam. And I'm confident now that you've watched this video, there shouldn't be too many surprises in these areas for you. So I wish you the best of luck in your studies.
Hi, this is David Voss, CCIE 11372, and in this video you're going to learn about advanced EIGRP. Specifically, you're going to learn about the engine or the algorithm that runs EIGRP, EIGRP messages, tables, and modules, and anything else that you really need to know for the CCDP architecture exam. So let's go ahead and begin. EIGRP is a unique protocol because it uses a hybrid approach combining distance vector and link state characteristics. Combining these features makes EIGRP very robust and allows for fast convergence even in larger topologies. Like RIP version 2, EIGRP is a classless protocol, and it allows for variable length subnet masks. Another similarity between the two protocols is their automatic summarization behavior. The algorithm that EIGRP uses is called dual or diffusing update algorithm. This is the engine that makes EIGRP such a powerful protocol. Dual operates based on a topology table that contains all the possible prefixes and information about how to reach these prefixes. You'll learn more about the topology table shortly. EIGRP is the only IGP that can perform unequal cost load balancing across different paths. This is accomplished using the variance command, which defines a tolerant multiplier that can be applied to the best metric, and that will result in the maximum allowed metric. For example, in this diagram, there are two routes with a cumulative metric of 100 to a destination and a route with a cumulative metric of 200 to the same destination. By default, EIGRP performs only equal cost load balancing, so it will send traffic across only the first two links, which have the metric of 100. If you wanted to send traffic over a third link, you'd want to set the variance to 2, meaning that the maximum allowed metric is 2 times the lowest metric, equaling 200. Traffic will then be sent proportionally to the metric, meaning for each packet sent over the third link, 2 packets are sent over the first 2 links because their metric is better.
EIGRP has 4 basic components, and these should already start looking familiar to you. It has messages. So messages flow to and from neighbors, EIGRP neighbors. There's 5 different types. We'll dig into that in a little bit. EIGRP has the dual algorithm. The dual algorithm takes the information from those messages and then processes best path and possible best path. Then all the information from the messages and the algorithms get put into tables. So these EIGRP tables hold the data from the algorithm and the messages. And then finally, the modules. These protocol-dependent modules support a variety of network layer protocols. So we're not limited. EIGRP is not limited to just IP. So with regards to messages, there are different types of packet formats. There's 5 different types of packet formats. First, there's the hello message. A hello message is basically a query out to anybody who'll listen, asking if anybody's out there. So a router running EIGRP sends hello packets by default, and it will send those packets out and hope for a return reply. And when it gets a return reply, it'll get that update. And that update contains all of the messages or all of the routes that want to be shared via EIGRP. Update messages are messages with a lot of routing information in them. And then there's the acknowledgement message, which surely you know about from other protocols, but it's simply acknowledging that, yes, I've received your message. And that's key to the reliable nature of EIGRP, which we'll talk about in a minute. There's a query message. So if EIGRP loses a route and does not know how to get there anymore, it will query its neighbors saying, do you have any information about this route? Because I'd like to get that information. And then if a router does have information on that route or on that path, it will reply back saying, yes, I do have information, and here it is. So these 5 messages can be broken out into 2 categories, some that are reliable and some that are not reliable. The reliable messages use reliable transport protocol, and this is unique to EIGRP, but RTP basically makes sure that packets get to where they're supposed to go in order. So an unreliable packet is a hello message. That message is not reliable, but the update message from an EIGRP router does use RTP. So it is sequenced and there are acknowledgments. So there is an acknowledgement to that message, but the acknowledgement itself is not reliable. Then there's the query message. Remember, the query is to ask, do you have information about this route? And that uses RTP, and the response to that query
the reply also uses RTP. So 3 different types of messages use RTP: the update, the query, and the reply. And I think that's critical to know for your exam. Now let's talk about the EIGRP algorithm, which is dual. Now, to understand dual, you need to understand what successor and feasible successor routes are. When you think of successor, just think of success. That's the best path. So if EIGRP loses connectivity to the best path, it will then run the dual algorithm and ask, is there a feasible successor? Is there a second best path? And if the dual algorithm states, yes, there is a feasible successor, a second best path, it will then promote that second best path to the best path. So that becomes the successor. Once it's the successor, it is then installed into the routing table. So for example, it would be installed into the IP routing table. And then the router would begin to use that new path. So this chart gives you an overview a high-level overview of how the dual algorithm runs. But it's important to know these concepts of successor and feasible successor as you move forward with EIGRP and how dual uses that information.
Now, as stated earlier, a key table to understand is the EIGRP topology table.
Topology table contains all destinations advertised by neighboring routers. This includes, remember, the successor and feasible successor routes, the best path to a destination and the next best path, respectively. So topology table is key for EIGRP to run. Now remember, within topology table, you can see the route tags. So in EIGRP, you can actually perform route tagging. And all you really need to know for now is that you can identify routes by their origination, which allows for custom routing. So you can tag those routes with a manual entry. So that's all you really need to know for now. But getting back to EIGRP tables, now, here's an example. We have, again, a hub and spoke design, router A, router B, and router C. Now, router A is going to build out, as soon as it enables EIGRP, it's going to build out these EIGRP tables. And one of the tables, again, is going to be this topology table. The topology table is going to contain critical information for EIGRP to run and make the choices upon what the best path is going to be. So in the topology table, it's going to insert routes that it learns from router B and router C. And then it's going to ask, now that I know about this route, which neighbor did I learn it from? And then finally, it's going to say, all right, I know the route, I know the neighbor I learned from, what metric should I assign to it? Which way should I send traffic or forward traffic? So in this example, the route itself, let's say we'll do a 10.1.1.0/24. And let's say we learn this route from both router B and from router C. So this topology table is filled out with 2 entries for the same route. Again, this is not the routing table yet. This is the topology table. And it has a metric, so let's keep it simple. So the metric to router B is 10, and the metric to router C is 20. So for this simple example, let's just say that the router now realizes that the successor route, the best route, is going to be the path through router B. Now, once the dual algorithm has run and it realizes this, it then takes that route or that path and it places the successor route into the routing table, in this case the IP routing table. So now we know the successor is to router B and the feasible successor path is to router C. So as we can see, it's going to choose the path out to router B. Now, what happens if this route information is lost and router A no longer learns about this route from router B or from router C and it gets flushed? Well, router A, what he's going to do is he's going to send a query to router B and to router C asking, do you know about this route? Because I've lost it and I'm hoping you have information on it. And the neighbors will respond back, but specifically, let's say in this case that router C is the only one that knows about it. Router C will respond, yes, I'm aware of it, and it will send the information over, and router A will say thank you very much, and router A will then insert it into the topology table. It will become the successor, and once it's the successor, it will be placed into the routing table, and then router A will then begin using the path through router C to reach that subnet. And last but certainly not least, we have protocol-dependent modules. So EIGRP and the dual algorithm function in a way that protocols can run and use EIGRP independently of one another. So IP builds out its own neighbor and topology tables. IPX and AppleTalk, they all build out their own neighbor and topology tables, and dual can work with any and all of them. So neighbor discovery and updates are a big part of EIGRP, and the best way I can equate this is if you have a new neighbor who moves into the neighborhood, you surely knock on his door and you introduce yourself and you tell him about yourself. Maybe you're married, where you're from, what your interests are. You tell the neighbor a lot about yourself, and if your neighbor is friendly, they're probably going to tell you a lot about themselves as well, like where they're from and what they're interested in as well. So in that initial conversation, a lot of information is exchanged. When you see that neighbor in the future, you don't give them all that information again. You just give them an update. You just say maybe what happened to you in the past day or so. So EIGRP pretty much works the same way. When two routers establish an EIGRP neighbor relationship, initially there is a major conversation where a lot of information is transferred between the two routers. And then there are follow-up conversations after that just have incremental updates. So the best way for me to describe this to you is actually just to draw this out. So let's say here we have router 1 and router 2, and let's say they're sharing the same point-to-point circuit, and both of the interfaces, directly connected interfaces for router 1 and router 2 are both participating in EIGRP. So router 1 sends a hello packet over to router 2, and router 2 receives that, and router 2 sends a hello message over to router 1. And this neighbor relationship now comes up in EIGRP. Now, initially, there is a large transfer of routes saying, hey, I have a lot of information to share with you. And router 1 says, you know what? You don't know anything about me. I have a lot of information to share with you, a lot of routes to share with you. Now, these hello messages continue repeatedly over and over. So the routers know that, hey, I know you're still around and I know you're still up and running. And they're consistently checking to make sure that they receive these hello packets. But let's say router 1 has a new update, a new subnet they know about. They're just going to send information on that subnet. Or let's say router 2 turns up a new interface and they insert that interface into EIGRP. Let's say 10.1.1.0, it's a /24. Well, router 2, when they send an update to router 1, they're just going to send this one update. So again, it's like the conversation with your neighbor. You're going to have one initial conversation about a lot of things, but then your follow-up conversations are pretty much just going to be updates. That's pretty much how EIGRP works. Now, the default for high bandwidth links, the hello interval is 5 seconds, the hold time is 15. For low bandwidth, the hello interval is 60 seconds, and the hold time is 180 seconds. But for the example here, let's say we need to know faster than 15 seconds if a circuit is down or a neighbor is down, and that we no longer want to forward routes, and we want to tweak that. Well, EIGRP allows you to do that. We can just log on to the interface, onto the router, and then configure the interface to change these intervals so that we are aware if our neighbor is down much quicker than the 15-second hold time. So the way you do that is that you go into the configuration, and then you go into the interface itself. So fast Ethernet here, fast Ethernet 1.1 is the interface on this point-to-point link. And IP hello interval EIGRP autonomous system number 10, and we're going to set that to 2 seconds. And IP hold time EIGRP 10, we're going to set that to 6 seconds. Now, This is important to note. Hello interval is important to note locally, but hold time is actually information we send on to the other router. And let's actually draw this out. I think it'll make a lot more sense for you. So here we have router 1 and router 2. And we have set router 1, the hello interval, to 2 seconds. So every 2 seconds, we will be sending a hello message over to router 2. Every 2 seconds. And again, we've adjusted that from the default 5 down to 2 seconds. Now, it's important to note we also set the hold time for router 1 to 6 seconds. And this hold time information is not actually held locally. We forward that over to router 2 to say, hey, you know what, router 2, if you don't hear from us in 6 seconds, then we're down. So here, we send you a hello packet. Router 2 counts down 6, 5, 4. Oh, I received a new hello because it's 2 seconds later. I'll begin counting down again. 6, 5, 4. I received another hello, and that resets my hold time counter, and I will begin counting down again. So every 2 seconds, these hello packets are actually resetting that hold time counter on router 2. Let's say router 1, the interface goes down, or the router goes down. Router 2 begins counting 6, 5, 4. He's not going to receive any hello messages. And he's going to count all the way down to 0, and he says, you know what, I haven't heard from you, you are down. That's important to note because now I'm going to flush your routes out of my table because I don't want to forward traffic to you anymore because it's probably just going to get dropped. And therefore, all of the information from router 1 is flushed out of the router 2 routing table. And that's important to know for convergence purposes, that you can tweak these numbers.
So here's what you've learned. You've learned about EIGRP algorithm, messages, tables, and modules, and any other key information you needed to know for your CCDP architecture exam. Good luck in your studies. Hi, this is David Voss, CCIE 11372, and in this video you're going to learn about advanced OSPF. Now actually some of what we're going to be reviewing you would consider foundational to OSPF, but being that you work with OSPF day in and day out, you begin to forget about some of the foundational aspects of OSPF, such as virtual links, router types, link state advertisements, the specifics of these topics, the fine details of OSPF that you may not be working with every day, but you certainly need to know for your CCDP architecture exam. So we are going to talk about OSPF functionality, router types, virtual links, link state advertisements, and area types so that you have the information you need to do well in your exam, but also obviously to manage your network. The OSPF protocol is one of the most complex routing protocols that can be deployed in modern networks. It is an open standard protocol and a classless routing protocol, so that allows it to support VLSM. It uses the Dijkstra SPF algorithm to select loop-free paths throughout the topology. OSPF is designed to be very scalable because it is hierarchical in nature, using the concept of areas to split the topology into smaller sections. OSPF generally does not converge as fast as EIGRP, but it does offer efficient updating and convergence, as it takes bandwidth into consideration when calculating route metrics, or what OSPF considers costs. A higher bandwidth generates a lower cost, and lower costs are preferred in OSPF. OSPF supports authentication and is very extensible, meaning that the protocol can be modified in the future to handle other forms of traffic. Now, we've covered a lot in the first couple minutes. Let's dig deeper into what we've talked about and get a bit more granular.
So let's start with administrative areas. So let's start from the basics here. Autonomous system is a network under a common network administration. Now, I'm sure you know that. But in OSPF, an autonomous system is broken out into areas. So areas are a group of routers that share a same area ID. And these different areas, these different groupings have different functions, and they know different types of information. So you have backbone area, standard area, etc., etc. And each of these areas perform different functions. So let's talk in detail about what some of these areas know and maybe what some of these areas do not know, but also how OSPF is designed around these concepts of areas. So remember, we're talking at a higher level here, but as a good rule of thumb, your backbone area in OSPF, if anybody ever refers to area 0, you know they're talking about the backbone area in OSPF. And this is probably the most well-known area because it is required. And all other areas must connect to the backbone area. So if for area to area communication, let's say you have an area 1 communicating to an area 3, both of those areas must connect to the backbone. So let's start here with a standard area. Now, a standard area, you know, what does that really mean? Well, standard areas can be thought of as equal opportunity employers, I guess you could say, because they know about every route in the autonomous system, in the OSPF network. And they share their routes, but they also learn all their routes from other areas through the backbone. And this is just fine. All of this route sharing is just fine if routers are high powered enough to store every route, but also to run these complex SPF calculations. But just know that standard areas contain LSAs of type 1, 2, 3, 4, and 5. Now next, you know, if you think of a stub area, which we'll talk about next, if you think of a network, you know, you have leaf nodes on networks. Well, that's what kind of a stub area is. It's handy if devices are lower powered, routers are lower powered, or simply do not need to know about every route. A stub area is similar to a standard area, but routers in it are not aware of externally sourced routes directly. And in terms of LSAs, that means that type 5 LSAs are not permitted in a stub area. Stub areas use a default route to exit. For traffic to exit a stub area, it uses a default route. Now, next would be a totally stubby area. And let's take this stub area concept one step further. In a total stubby area, in addition to the lack of type 4 and 5 LSAs, type 3 LSAs, which carry information about internal routes, are also prohibited. The concept of an injected default route still applies here, just like a stub area. So all traffic leaving the area does so using the default route. And then finally, let's go over this concept of not so stubby areas. So, you know, this is an interesting, I guess you could say, concoction, because not so stubby areas can connect to non-OSPF networks that are not a part of this autonomous system, and they can receive routes from those non-OSPF networks or networks that are not participating in the autonomous system. And it will receive those routes through redistribution, and then it can turn those type 7 LSAs and kind of, you know, basically it's going to mask them and make them appear as type 5 LSAs, and then begin sharing them onto the network. So there's your ideas of networks in areas, but all areas in an OSPF autonomous system must be, as you know, physically connected to the backbone area. Well, what if you can't do that? You know, what if you can't connect an area to area 0? So let's draw out this concept of a virtual link. Let's imagine we have a company on the East Coast, and in this company we've deployed OSPF already. So we have our backbone area 0, and then we have other areas that have to obviously connect into this backbone area. So let's say we have an area 1 in the Boston area, and then an area 2, let's say in Florida. But let's focus in on area 1. So in the Boston area, we have area 1 in Boston, and we acquire another company in that area. And it's easy enough for us to connect this new company into our Boston resources. So we're going to connect them into our Boston router very simply. The problem is that even though this company that we've acquired, maybe they're already running OSPF, and we convert them to OSPF area 3 to work within our autonomous system, we still need to meet the requirement of OSPF where an area must connect into area 0. So OSPF allows for what is called, as you know, the virtual link. We will create this virtual link between area 3 and area 0. It's passing through area 1, and this allows us to meet that design requirement of OSPF. So route to area 3 and area 0 see this as a direct connection, and things will work just fine thanks to the virtual link. So there are many different OSPF router types that you need to be aware of. There's the area border router, which connects one or more OSPF areas to the backbone area. There's the ASBR, or Autonomous System Boundary Router, which will be located between an OSPF autonomous system and a non-OSPF network. And then you have your backbone router, which is pretty straightforward, a router with at least one interface connected to area 0. And then another easy concept, an internal router, a router with all interfaces in one area. Let's draw this out real quick, to drive it home. So let's draw out our area 0. And in area 0, you know already, is the backbone. So a router within area 0 is a backbone router. And then we connect to another area, let's say area 1. This is an area border router. Pretty straightforward concept. There's your ABR. And let's say we have another area we're connecting to. There's another ABR. But we are also connecting an ASBR here because we have a non-OSPF network that we're going to be injecting routes from into our OSPF process. So we are injecting routes in through an ASBR, converting type 7 LSAs to type 5, and those are being forwarded on to the network. And then you have, last but not least, internal routers, which have all interfaces in the same area. Pretty straightforward. So in order for two OSPF routers to communicate, they need to go through this process of exchange states. So you need to understand a basic concept of what these are. Here's the following states. There's the init state, where a hello packet has been sent by a router, it's waiting for a reply. Then the establishment state, where there's the discovery of that hello, and then the election of a DR on multi-access networks. The XStart stage, where a master-slave relationship is started between two routers. The router with the higher router ID becomes the master and starts the exchange, and as such is the only router that can increment the sequence number. Then there's the exchange state, where the slave acknowledges the master's packets, and this information in this state is only LSA headers, and it describes the contents of the entire link state database. Then there's loading, where there's a request for more information. In this state, the actual exchange of link state information occurs. And then there's full synchronization, and in this state, routers are fully adjacent with one another. All the router and network LSAs are exchanged, and the router's databases are fully synchronized. Now, a designated router in OSPF is a key concept that you need to know, because on multi-access networks, a designated router will establish adjacencies with all other routers on the multi-access network, learn all of their routes, and then share all of their routes with all the other routers. And then the BDR, the backup designated router, will fill in should the DR fail. And you can set the DR and the BDR manually, and actually you should do it this way. You should set it using the priority command in OSPF. So understanding OSPF priority is key because you can manually set who the DR is and who the BDR is. Now, it's easy to talk about this and look at a PowerPoint, and you may not fully appreciate how important this concept really is. So let's actually draw it out. So on a typical multi-access network, let's say we have 5 routers and you want to establish adjacencies in OSPF to share routes between them. If they did it that way, where they're all neighboring with one another and communicating with one another, you're going to see that all of these adjacencies are going to add up pretty quickly. And that's going to tax the resources on the routers themselves, but it's really unnecessary. We can share this information in a much more efficient manner. So what we're going to do is we elect a DR, and OSPF, again, has this built in within the OSPF design itself, where multi-access networks, you can elect a DR, and then the DR establishes an adjacency with all the other routers on the multi-access network. It learns all of their routes and then shares all of their routes. So now we just have 4 adjacencies required. Now, if the DR fails and those adjacencies fail, the BDR would take over. Now, regarding link state advertisements, what you really need to know, at least just for now in OSPF, is that a link state advertisement is a packet that contains all relevant information regarding a router's links and the state of those links. Now, there are many different types, and I've listed the key types for you here. And we're going to dig into detail on these different types as we get into the labs. But just for now, know that these are informational packets that have information on a router's links and the state of those links. So now that OSPF has gathered all this information, it needs to know what to do with it. It needs to choose best path. So it puts all the information in a topology table. And then OSPF, the metric for OSPF is cost. So cost is 10 to the power of 8 divided by bandwidth, and lower costs are preferred. So the best way to understand cost is actually for us just to draw this out to see how it works. So let's draw out a 6 router network. And let's say we have router 1, which ultimately wants to communicate with a network off of router 6. And it will have 2 choices, 2 paths it can possibly take. It can go via router 2 or via router 4 to this network. We'll say 192.168.10 network/24. Which is hanging off router 6. Now, router 1 then calculates using OSPF the cost for each and every link in this path. And it's going to do the same for the path from router 2 and 3 to 6. And then what OSPF is going to do is add up the entire cost to get to router 6. So from going via router 4, that path has a total cost of 20. And going via router 2, that path has a total cost of 25. And we know that OSPF uses the lower cost to make its decision on which path to take. So the total cost of 20 wins out, and we will choose router 4. Now that being said, let's say a new network is introduced that has higher bandwidth links. And even though we have more routers or more hops through this network, let's say there are 4 hops. If the cost is low, and for this case we'll say 5, 5, 1, 1, and 1. If the total cost here is just 13, even though there's more hops, OSPF is going to choose this path because it's more efficient. So that's cost basically explained. That's cost in a nutshell.
So here's what you've learned. You've learned about OSPF functionality, router types, virtual links, link state advertisements, and area types. All this you'll need to know for your CCDP architecture exam, and I wish you the best of luck in your studies. Hi, this is David Voss, CCIE 11372, and in this video we're going to be covering advanced BGP. Specifically, we're going to cover the necessity of BGP, then we'll dig into BGP functionality, path vector attributes, the scalability of BGP using route reflectors and confederations as well. So let's begin. BGP is used to route between autonomous systems and is considered to be a path vector routing protocol. Routing decisions are based on multiple attributes that can be tuned and controlled, resulting in the particular path the AS's data will take. This is more of a policy-based routing approach, and policy routing is very important for internet service providers routing traffic between each other for different ASs. BGP is a classless routing protocol, and it supports VLSM and summarization. While IGPs can scale to thousands of routes, BGP can scale to hundreds of thousands of routes, making it the most scalable routing protocol ever developed. Another characteristic of BGP is its high rate of stability. As there is never a solid convergence of the internet routing table, that is, something is always changing in such a large routing table, this is obviously very important to be stable. In addition, it is stable enough to handle routing and decision making at the same time. Because BGP focuses on the enforcement of policies, it does not use a simple metric value that might be tied to a single parameter. Instead, BGP has a group of attributes that can be manipulated to dictate a particular routing policy, and you will learn about all of those attributes in this video. When used to exchange routing information between organizations, BGP can be configured in two particular ways. As a transit network, that is, when ISPs want to provide transit to other destinations on the public internet, or a multi-homed network. Big enterprise networks that rely heavily on internet traffic and have sophisticated connectivity requirements would use this methodology. If the connectivity connects to two or more ISPs, BGP allows them to control inbound and outbound routing policies. Most of the enterprise networks do not need BGP. This can be for various reasons. First, the network requires single ISP connectivity, and default routing is sufficient. A default route will simply point to the ISP, so all internet traffic is routed out that single connection. Memory and CPU resources are limited and do not support BGP implementation. Since the global routing table needs more than 1 gig of memory just for storage, obviously not every business will have that much memory or capability. Finally, not owning the IPv4 address space in use. This happens in situations where the organization's addresses are owned by the ISP, which is a frequent occurrence for small and medium-sized organizations.
Now, regarding BGP path attributes, there are some that you absolutely have to know and memorize. The first is weight. Weight influences a best route for the local router, and obviously it's manually configured. Local preference influences the best route for all routers in an autonomous system, so this is a shared attribute. AS path lists the number of autonomous system numbers in the path, and this can be manipulated. Origin is a value implying if the route is from an IGP or an EGP. And then finally, the MED, which can influence the best route for routers in another AS. So you can influence traffic flows into your AS by sending out the MED to other routers. So here you can see we have two routers that are in autonomous system 700. And then upstream, we have another router in autonomous system 140 and autonomous system 87. So here you see there are 4 hops. But as far as BGP is concerned, it's just counting ASs. So it counts 1, 2, 3 ASs. The AS path is 700, 140, and 87. Why is this important to know? Because here's another flow that has 2 routers in AS 700 and then 1 router in AS 87. Now, according to this path, there's just 2 ASs. That would be the preferred path. It's critical to understand that BGP is concerned about AS path and not so much about hop count. AS path is a key attribute to understand. Now, internal versus external BGP. iBGP is something you would run basically interior to your company. It's BGP connectivity within the same autonomous system. In this, routers do not update AS path. Normally they should never have to because you're running the same autonomous system. And in iBGP, things should always be meshed. Routers should always be fully meshed. And there are ways you can get around this, and we'll talk about that in a little bit. Now, eBGP is external connectivity to other ASs. And routers do update the AS path in those cases. So let's say we have an autonomous system 200, and in our company we're running iBGP full mesh between all routers. And let's say we have connectivity to 2 upstream providers. One is autonomous system 301 and the other provider is autonomous system 450. Now, between ourselves and our providers, we are running eBGP because it's 2 different ASs. And internally, we are running iBGP because we are communicating between the same AS. Now, configuration between iBGP and eBGP is quite similar. The main difference is you're choosing to communicate with the same AS or a different AS. Now, let's say we want to communicate to a web server over the internet, and we have a certain amount of hops. Now, let's say one of those paths through AS450 takes us through quite a few more hops, but it takes us through fewer ASs. So let's just say, for example, we go through AS900 and then AS100. So that's 450, 900, and 100. Those are the 3 ASs we traverse in order to reach that route. Now let's say on this flow through autonomous system 301, we go through fewer hops but more ASs. Now, even though there's fewer hops, because there are more ASs, we're not going to prefer this route. There are 5 ASs in this path. That is not going to be preferred to the other path, which has only 3 ASs. So we're going to choose that path. We'll choose the 3 AS path. Now let's say we're running a web server inside of our company, and we're running iBGP between these 3 routers, and we're connecting to 2 upstream providers using eBGP. And let's say we have users on the internet who are trying to get to this web server. We can manipulate the AS path attribute in BGP to make them prefer one path over the other. And the way we do that, now let's say our autonomous system is 50, we can manipulate the AS path attribute by adding to the AS path on one of our links. So, for example, the users know that they can reach the web server via one AS. Well, we're going to increase that on the top router, and we're going to manipulate it manually and add our AS over and over again to the AS path attribute. And the users, as far as BGP is concerned, that now is a longer path, and therefore the users will prefer the bottom path because it's only one hop, one AS hop. Now, if that router were to fail, users would then prefer the other path. So you see, you can manipulate traffic flows that way. Now, you need to understand the concept of public and private ASNs, and this shouldn't be foreign to you because you understand public and private IP addressing. So autonomous system numbers are chosen from this pool, and you can use them for private use or public use as need be, but you should be aware of that chart. Now, regarding BGP updates that we receive from neighbors, you can receive from your provider a default route only, which many people do, or you can receive a full BGP routing table. That is literally every route that's available on the internet, or you can receive just partial updates, and that is maybe the provider knows about certain routes via a better path than most other providers. You can just receive a partial update from your provider. So you should know that you can receive those 3 different types of updates. That should be known for your CCNP route exam. Now, regarding advertising routes, advertising BGP routes can be done 4 ways, either through the manual network command, redistribution of BGP into IGP, or propagation of existing BGP routes, or again, manually using the aggregate address command. Maybe the best way to explain these is to simply draw it out. Now imagine we have a router with an iBGP connection and an eBGP connection to an upstream provider. So there's our eBGP connection, here's our iBGP connection, and we're autonomous system, let's say 400. So on a router, we can advertise in 4 different ways. We can manually specify the network we want to advertise by literally typing it in, network 10.10.10.0 or network 198.110, and we can forward that via iBGP and or eBGP. The other way is we can learn routes via BGP and redistribute that route into, let's say, an interior routing protocol. Let's say if we're running OSPF, we can take the routes we learn from our eBGP neighbor and redistribute them. The other way is to simply pass the routes we're learning from our eBGP neighbor via BGP internally to our iBGP neighbor. So that's just forwarding the information on. And finally, we can again manually set an aggregate address on the router, and that's a manual configuration to aggregate some of the routes. And again, that can be advertised out either way. So the rule of synchronization in BGP, you should simply know this, that BGP will not advertise a route unless it knows about that route via an IGP. That's what you really need to know for the exam. Now you can disable this by typing no synchronization on your router, and then it will simply forward routes that are not in the IGP.
So here's what you've learned. You've learned about the advanced BGP information you need for your CCDP architecture exam, including its necessity, its functionality, path vector attributes, and its scalability through route reflectors and or confederations. Good luck in your studies. Hi, this is David Voss, CCIE 11372, and in this video you're going to learn about IPv6 routing. Specifically, we're going to focus in on RIP, OSPF, and EIGRP changes to support IPv6, with the understanding that ISIS and BGP underwent the least amount of modifications to support IPv6 because they were built with extensibility in mind. Cisco routers do not route IPv6 by default, and this capability should be activated with the IPv6 unicast routing command. Cisco routers are dual stack capable by default, meaning they are capable of running IPv4 and v6 simultaneously on the same interface. IPv6 allows the use of static routing, and it supports specific dynamic routing protocols that are variations of the IPv4 routing protocols modified or redesigned to support IPv6, such as RIP Next Generation, OSPF version 3, and EIGRP version 6. We will talk about each of these routing protocols individually. Before we do that, let's talk about what they have in common. RIP-NG, OSPF version 3, and EIGRP version 6 are new routing protocols that work independently of the IPv4 versions, and they run in a completely separate process on the device. BGP and ISIS are exceptions to this rule, as they route IPv6 traffic using the same process used for IPv4 traffic, but they use the concept of address families that hold the entire IPv6 configuration. Many of the issues with IPv4 still exist with IPv6 routing, such as name resolution and non-broadcast multi-access environments. An important aspect is that IPv6 routing protocols communicate with the remote link local addresses when establishing their adjacencies and exchanging routing information. In the routing table on an IPv6 router, the next hops are link local addresses of the neighbors. As mentioned, static routing is one of the options that can be used in IPv6, and it has the same implications as in IPv4. A route can point to the next hop, a multi-point interface, or a point-to-point interface.
To support IP version 6, all of the IPv4 routing protocols had to go through adaptations. Each had to be changed to support longer addresses and prefixes, and the actual messages used to send and receive routing information have changed in some cases as well, using IPv6 headers instead of v4 headers. But in particular, like their IPv4 versions, each version 6 IGP uses v6 multicast addresses. Those are just a few of the changes, but even with those changes, each IP version 6 IGP has many more similarities than differences compared to their respective version 4 cousins. Let's start with RIP. The overall operation of RIP Next Generation closely matches that of RIP version 2. Routers still send periodic full updates with all routes. No neighbor relationships occur. The continuing periodic updates also serve the purpose of confirming that the neighboring router still works. The big difference between RIP version 2 and RIP Next Generation configuration is that RIP Next Generation discards the age-old RIP network command and replaces it with an enable interface subcommand. Finally, RIP Next Generation allows multiple RIP Next Generation processes on a single router. So an iOS requires that each RIP Next Generation process is given a text name that identifies each RIP Next Generation process for that one router. Next, let's talk about EIGRP. Cisco originally created EIGRP to advertise routes for IP version 4, IPX, and AppleTalk. This original EIGRP architecture easily allowed for yet another Layer 3 protocol, IP version 6, to be added. As a result, Cisco did not have to change EIGRP significantly to support version 6, so there are many similarities that exist between version 4 and version 6 versions of EIGRP. Now regarding OSPF, in order to support IP version 6, an IETF working group took the OSPF version 2 standard and made changes to the protocol to support version 6, resulting in the new protocol named OSPF version 3. To migrate to IPv6, routers run OSPF version 2 for v4 support and version 3 for IPv6 support.
So here's what you've learned. You've learned about the updates required in routing protocols for IPv6 support. And then specifically, we dug a little bit deeper into RIP Next Generation, OSPF version 3, and EIGRP version 6. This is the information you'll need to know for your CCDP architecture exam. Good luck in your studies.